We have an expert in liquid flows on space, Dr. Mark Weislogel from the Portland State University in Oregon is the principal investigator for the CFE experiment. Mark, welcome to Mission Control Houston.
Greetings from Portland.
Hey, thanks for joining us again. And let's start off with the basics of what you guys are working on with capillary flow on the space station.
Well, currently we have a set of these handheld experiments. The acronym is CFE, and they are performed by the astronauts on what's a movable workbench that's on the space station. And they configure this container up and set up lighting and cameras and talk to us on the ground, and they deploy a fluid into a strange container shape where the geometry of the container interact with the surface tension and wetting properties of the fluid to make the liquid go where we want them to go. And this is an important aspect of designs for fluid systems on spacecraft, because you can make the container basically pump the liquid where you want them to be. And what we're trying to do is develop a theoretical basis to use such forces to replicate fluid behavior in space, just like it would happen on ground, but you're replacing the impact of gravity with that of surface tension. And so engineers could be much more familiar with systems and make them more reliable.
Mark, you called it weird shapes that you were putting these fluids through when we talked earlier this week. Can you tell me a little bit about how these shapes are designed and what you're trying to find out there?
Yes, the shapes actually arise from mathematical relationships. So we identified these different families of geometries that make the fluid do different things at different rates. And so they have different names. They're tapered triangular vessels or tapered rectangular vessels, or cylinders with vein structures that taper, or strange teardrop-shaped sections, these kind of things. And so what you're used to seeing, like cylindrical tubes or spherical tanks, start to look more like the innards of a body digestive system. The new shapes are kind of strange. But it gets these really neat results of passive manipulation of large amounts of liquid in space.
And why do we have such a problem with that?
Well, if the problem is that you can have multiple. Okay, if you have a container in low gravity, the liquid could be located in various places within the container. It would be nice to design shapes that there's only one possible place that the fluid could be, and it's where you want it to be. That's what we're after. The nature of the mathematics that governs this stuff is that you have multiple solutions, many different solutions. So we're trying to make that a lot easier.
And I would imagine that this would probably help in the development of systems that could rely on natural flows instead of hard-to-maintain pumping systems.
Exactly. So we would like to get away from the added complexity of centrifugal, pumping or separations, and that require orbital maneuvers or even spinning the spacecraft, things like that, and greatly simplify things so that the fluid just always goes to where you want it to go, so that the center of gravity of it is known. All of these things are known. That would be great. Also, it would be good if, even if you do use such a thing as a centrifugal method, if there's ever a failure, you have this backup passive means of still being able to hobble along functioning, maybe at a reduced level, but you'll still function with no moving parts in a passive manner. So it's a nice redundant system as well for systems that already use something like a centrifuge.
And we're already using some of this capillary flow on the space station, right?
Yes, that's true.
And systems like the cooling system, particularly outside with the ammonia that's used to help get rid of excess heat.
Yes, that's designed to be. I believe is that a single phase? I can't recall if that's a single or a two-phase system. I think it's a single-phase system. So not always do we rely on surface tension, but in some manner it still winds up rearing its head and can either bite us or we can exploit it. So there's we must understand this to make systems reliable, that we can count on their performance.
And as I recall, you have a student team that's involved in doing this work too, right?
Yes.
Could you tell us a little bit more about how many students you have working with you and the learning experience this provides?
Yes, this is probably the greatest part of this work is yes, we have I have 3 students currently now working on this particular project, and these students have been involved in training astronauts and helping develop the crew procedures to actually talking with the astronauts during the operations. One of those students, who's now a PhD student at Portland State, Will Blackmore, has completed over 10 uh, sessions discussing with the astronauts during the experiments. This is through a control station that NASA allowed us to set up at our campus. This experience is really something. He's very good at it too, and I rely on him a lot to take some of the pressure off me, because it's intimidating, if you ask me, especially when you're excited about the experiment and the things that can go wrong and the possibility of getting the data in just moments. Oh, it's very exciting.
And you told me earlier this week that you all have been on a different sleep schedule because the space station operates generally on Greenwich Mean Time, which means they get up at midnight Central Time here in Houston, and you're 2 hours earlier out there in Portland. How's that been working out for you?
It works out, and we've gotten used to it. But when we bring new people onto the team, they can experience difficulties. I think we've had 10 all-nighters, already, just in the last few months, and so it's something to try to live a normal day, working pretty hard, and then all of a sudden, here goes an all-nighter. But a little caffeine and the enthusiasm keeps us going.
Have you seen anything that surprised you on CFE3 so far?
Oh yes, we do not anticipate this. So, but we're growing to expect, some well, you could call them discoveries, some new things that we didn't imagine, like when the astronauts will manipulate the test cell in ways that, we learn on the spot that we can do something different and get new data, better data, more data, and in some cases we see fluid doing things that we don't expect at rates we didn't anticipate, and those are the ones we scratch our heads, and sometimes we say, we should have thought of that, but sometimes we say, that's new. Let's go after that. So what we discover can change what we discover. But fortunately for us, in our cases, it's always been expansive. So everything that we've observed improves our science to a high degree. It's been great.
And tell us a little bit about yourself, Mark. I know it's all about the math, but give us a little background of your education and where you're from so that we can help folks identify with the real people involved in the experiment in space.
Okay, well, I was pretty much a snoozer in high school, but I got turned on in college to fluid mechanics at Washington State University, where I got both undergraduate and master's degrees. And that's when I first saw microgravity fluid mechanics, and that really changed things for me. I wound up getting a PhD at Northwestern University and working at NASA Glenn Research Center for 10 years, and that's where I got fascinated with microgravity work. Since then, have come to Portland State University, where we just recently built a drop tower in support of the microgravity work, and it has really been just a series of discoveries and novelties and developing the science. And now we're into this application mode where we're applying things to systems on the ground, microfluidic systems, from something as simple as candle flame wicks, structures to actual processing of blood samples, things like that. And as well as applying our work to developing better systems for spacecraft too. So we're really enjoying this.
Well, Mark Weislogel from Portland State University, I want to thank you again for being with us here today to talk about Capillary Flow Experiment 3, and we look forward to seeing the benefits of your work in the everyday things that we use here on Earth.
That would be great, wouldn't it?
Thanks again, Mark.
Okay, see ya.